Hi there, in this video we're going to talk about the natural exponential function and the number e. So what is the number e in the natural exponential function? So the natural exponential function is f of x equal to e to the x. So we have already looked at what does f of x equals 2 to the x look like. And so when we graphed this, we saw that any exponential has a horizontal asymptote and a y-intercept. So it's characterized by a horizontal asymptote, in this case 0, and a y-intercept of 0, 1. And so what makes this different from, say, 5 to the x is that at 1, this one, the value is 2. If I wanted to graph f of x equals 5 to the x, I'm still going to have my same y-intercept. If you find the y-intercept, set x equal to 0, you're going to have y is equal to 5 to the 0, which is 1. So we're still going to cross there, but now we still have 0 as the horizontal asymptote, but now it's going to go increase faster. When x is 1, this is not drawn to scale here, this is going to be 1, 5. And so that's what makes these two different. The bigger the base, right? The base is the 5, so if I make it 7, this is going to go even faster at 1, right? If it's going to be, instead of, notice that 1 here, we go 1, 2, then 1, 5, then it's going to be 1, 7. So it's going to go much, much higher. So it's going to grow. So e to the x is going to have the same characteristics. So it will have a horizontal asymptote and a y-intercept. But what is e? Right? I know where to put when I have 2 to the 1. I know that's 2, and I know where to plot it. When I have 5 to the x, 5 to the 1, right? If x is equal to 1, then I'll go y equals 5 to the 1, which is 5, and I know where to plot that. That is 0.15. But how do I plot the point 1e? So what is e? Is really what we're trying to answer. And so to find out what e is, we're going to go back and look at our compound interest formula. So our compound interest formula is a equals p 1 plus r over n to the n t, where p is the principal, r is the interest rate, or the rate of change, and then n is the number of times compounded in a year, where nt is the number of years. So to find what the number e is, what I'm going to do is I'm going to ask you, suppose that you invest $1. So we're going to start with, one of our quantities be easy to compute. Suppose we invest $1 and it's, at the end of the year is going to double. So and it doubles at the end of 1 year. So what was the interest rate? But at the end of the year, you have $2 now. So that means that the interest rate was 100%. So 100%, when you write it as a decimal, that's 100 over 100, which is 1. So let's see, how do we get the $2? So I'm going to have A is equal to the principal, which is 1 times 1 plus r over n. R is 1 to the nt, right? But t is also 1. So this is my formula. So if I do it just once per year, it's compounded once per year, that means that n is equal to 1. And so this is how I get my 2. A is then 1 times 1 plus 1 over 1 to the 1. So I get 2. So at the end of 1 year, we get $2, which we don't have to do this formula because we can say, well, if it doubles at the end of the year, and I started with $1, of course I'm going to get $2. But what if we instead of compound it annually, right, once per year, what if we compound it semi-annually? So let's try the formula. What if semi-annually? So the amount then, am I still going to get $2? Well, let's find out. It's still my $1 times 1 plus 1 over, now semi-annually, so that means twice per year. And to the n times t, so times 2. And I'm still doing just 1 year, so but twice per year. So now I have 1 plus 1 half square. And 1 plus 1 half, what's that? 3 halves square. So I get 9/4, which is 2.25. So now notice that by compounding semi-annually, I gain a quarter. So it's not just $2. My money didn't just double. Now I get it double and I get a quarter. So then it's like, okay, what if then if I do it, what about quarterly? Actually, let's do monthly, just to increase it a little bit faster. So what if we compounded monthly? What happens to our dollar? So I'm going to have A equals, the amount is my $1 times 1 plus, the interest rate is still 100% over, but now in 1 year I'm compounded monthly, so that means 12 times to the NT, so 12. I'm still looking at just 1 year. So this is 1 plus 1, 12 to the 12. So 1 is 12 over 12, so I get 13 over 12 to the 12. And when you put that in a calculator, I got 2.61303. Okay, so I get my $2.61. So then what if we keep going? What if I do it daily? What if I compound that dollar daily, right? So that means that instead of so let's go back and see what we've done. So we said you invest $1, and if you just compound the interest once in a year, your money doubles. And then we said, okay, take that dollar. What if we compounded twice a year? So we're going to earn interest on that dollar instead of just at the end of the year. We earn it twice in 1 year. So that makes us gain a quarter. And then, so notice that it increased pretty fast, right? It went from $2 to 2.25. And then from 2.25 going monthly, now I have $2.61. So what about daily? So if we apply the interest to our $1 every day, what happens? So there's 365 days in 1 year. So 2 to 365, and so we can kind of see a pattern there. So 365 over 365 plus 1 gives us 366 over 365 to the 365. So put this in a calculator and we get 2.7145. So, okay, so we went from $2 to 2.25 to $2.61. Now it didn't increase too much. So we gained another 10 cents by compounding daily. What about hourly? What if our money compounds, if we gain interest every hour? So how many hours are in a year? There are 8,760 hours per year. So that means that our amount is going to be, I'm going to stop writing the 1 here. So 1 plus 1 over 8760 to the 8760. So you kind of see what's happening here. When I put this in the calculator, I'm going to get 2.718126. So I didn't increase very much anymore. And my compounding is getting a lot higher. So so you can see what we're doing. So once a year, then twice a year. What about 12 times a year? What about daily? What about hourly? What if we compounded it every second, every nanosecond? So what's happening? So if we did it every second, right? How many seconds are in a year? This is a really huge number. So I'm just going to say approximately 31,500 or 31,500,000 seconds in a year. This is an approximation just so we can do this math real quick. So it's going to be 1 plus 1 over 31,500,000. And again, this is an approximation to the 31,500,000 seconds. So this will give us, you put this in a calculator, and it's not going to give you an error. You can try it, put in your calculator, you're going to get 2.71828. Notice that the first three digits are exactly the same. And so if our dollar gets compounded, and then what about every nanosecond? What about continuously? So if you don't stop compounding, if you don't take breaks in compounding, like semi-annually, means we compound it at the 6th month, and then we take a break, and then we compound it again at the end of the year. Monthly, we compound it the first month, then we take a break, compound it the next month, and so on. So what if we don't take any breaks? So that's what continuously means. So if we continue to apply the interest without taking any breaks, that's what compound continuously means. Then this number, notice that it's getting higher and higher and higher. So when I say a is equal to 1 plus 1 over n to the n, my n getting higher means how high? Getting larger and larger. So going towards infinity. So as n goes to infinity, can you guess what this number is going to? Notice that I have 2.71826, 2.71828. If you try another number here, you're going to see that it's not going to change much from that. So this number is equal to 2.71828, 459045, and so on. And this is what we call the number E. So E is a number kind of like pi is 3.14. So the approximation for E oftentimes is that E is 2.718. So this is the approximation for the number E. So just like pi is an irrational number, E is also an irrational number. It doesn't repeat. So that's what the number E is. So now when we graph f of x equals e to the x, well, 2.718, so now I know something about E. E is a number that is larger than 2, but is less than 3. So if I graph f of x equals 2 to the x, g of x equals e to the x, and h of x equals 3 to the x, we can kind of see where e to the x is going to fall. So let's try it. So when I graph my 2 to the x, I know it has a horizontal asymptote. It crosses at 0, 1, and it goes on to infinity. We have our y-intercept is at 0, 1, and when x is 1, this is the point 1, 2. So I'm going to graph 3 to the x. So h of x equals 3 to the x is the y-intercept is still going to be at 0, 1, but now when x is 1, we're going to be over here at 3. So this will be a point 1, 3. When x is negative 1, right, if I do it for 2 to the x, this will be negative 1, 1 half. And for 3 to the x, we're going to be at 1/3. Negative 1, 1/3. So it's going to be down below here. So we have a same horizontal asymptote as 0. And then we're going to cross our y-intercept, and we keep going like this. But a little bit better graph. I need to take art lessons or something. So this will be what our 3 to the x looks like. So e to the x is, because e is 2.71828, this is a number between 2 and 3. When I graph e to the x, right? My y-intercept is going to be the same, 0, 1, but now at 1, it's going to be over here at E. And so this is going to fall in between these two graphs. So that is my e to the x, with the point there being the point 1e. And e, we saw from above, is 2.71828. 182845945. That's just the first 16 digits of it, but the approximation that we use is E is 2.718. So that is the number E. So E is used when you have continuous, when something is compounded continuously. So some examples of things that compound continuously would be population growth. Right? There are no breaks in when babies are born. Babies are being born every second, every nanosecond, is continuously all around the world. So the world population is something that compounds continuously. Bacterial growth, the way that a virus grows, that's continuously. Same with decay. When you're trying to, like a bacteria decays, it compounds continuously. So those are examples of things that use the number E. And so we're going to get into applications of the number E. To evaluate it using a calculator, you should see the number E on your calculator is above the button. So on your calculator, you'll see a button that says ln, which is the natural logarithm. And then above it, you'll have e to the x. And so this is the natural exponential. So those are inverses of each other, and we'll talk about what an inverse is. And if any of you are interested in knowing how I know so many digits of the number e, right, I said it's 2.718281828459045. Notice that if you put e to the 1 on your calculator, the calculator is not going to give you this many digits. So if you're interested in knowing how I know so many digits of the number e from memory, because I do have it memorized, email me or do a live Zoom office hour with me, and I'll show you how. It's pretty cool. All right, bye.